So in the morning, we have reached to this state of the equation where we did the variation of pressure with respect to the thickness. So from this I want to proceed in order to get the final version of the equation, because it involves few expression into the Taylor series, so we have to approximate some function. So I'm going to do this in order to get the final one. Okay, so the first one is that we have to get the approximation of 1 minus 1 by beta. So actually this can be written as 1 minus beta raised to minus 1, correct? So from the Taylor series of expansion, that if we have some function like 1 plus x raised to n, then it can be expanded, or it can be approximated, or it can be expanded to 1 plus nx plus n minus 1 x squared plus divided by 2 factorial, like this. Okay, so we are going to expand this into this format. So we know that here n equals to minus 1 and plus x is my minus of beta. So I will get this as 1 by 1 minus beta equals to 1 minus beta raised to minus 1 as something like 1 plus minus 1 times minus beta plus minus 1 minus 1 minus 1 minus beta whole squared divided by 2 factorial, like this, right? I can expand this in this format, and you can see this gets around 1 plus beta plus this one as you can see 2, right? So 2 get cancelled, so beta squared, like this. So that you know this beta is very small, this is equal to this, right? So if you ignore the higher order terms, then I can approximate this as 1 plus beta. So I'm going to use this result. Again, I have to modify this portion as like this. I want to say that define x here. I want to define this x as ln h upon h naught, correct? So this is now, I can write this as e raised to x equals to h upon h naught, correct? And if I inverse this, I am going to get e minus x will be h naught over h. By using this relation, you can see here, by using this relation, what I can do is I can modify this. I can insert here and modify this, and I can write this as, now our equation became, after approximation, p h equals to sigma 1 plus beta. Okay, I'm using this result here, this result. Then I'm getting is 1 minus beta. Then I have this h naught divided by h, which is minus ex, correct? Then I have h upon h naught. H upon h naught is ex. Then I have is this beta, right? So I can get is e raised to x, then beta, like this. So this is the change that I made by using this substitution. If you see this carefully, this one is in the form a raised to n and a raised to m, which we can write this as a raised to m plus n, which is power law, right? Power law of exponent. So I can write this as e raised to minus x, e raised to x beta, as I can say minus x plus x beta, which I can write as e raised to minus x 1 minus beta. I can write this, right? So I am writing this now as p h equals to sigma 1 plus beta 1 minus beta. Now I'm going to write this minus x 1 minus beta, like this. Now I also want to approximate this in the form of like this. So we have Taylor series expansion of e raised to x as 1 plus x plus x squared by 2 factorial plus x cubed by 3 factorial, like this, right? So if this x is very small, I can approximate this e raised to x as 1 plus x. High order terms, I can ignore it, correct? So by doing this, what I can get is e raised to minus x 1 minus b can be written as 1 minus x 1 minus beta, like this, plus then other terms. So this can approximate to this term. If I substitute this result here, then I'm able to get this ph equals to sigma 1 plus beta. Then I'm going to say beta, I'm going to substitute this 1 minus x 1 minus beta. Now I'm going to also expand this into the term, so I'm getting is x 1 plus beta 1 minus beta 1 minus x plus x beta, correct? This x beta. Then again I want to get this and say sigma 1 plus beta 1 minus beta plus beta x minus x beta squared, correct? And again I am going to ignore this term because it is higher order term, so I'm going to ignore this term and write this as sigma 1 plus beta 1 minus beta plus beta x. Now I'm going to expand this term by multiplying this, okay? So it will be now sigma equals to 1 minus beta plus beta x plus this one beta minus beta squared minus again beta squared x. So here also I'm going to ignore this higher order terms because they are very small, and then this and this get cancelled off, and I'm left with sigma 1 plus beta x is equal to ph, okay? So if you see this carefully, this is actually approximation of e raised to 1 e raised to beta x, correct? This can be approximated into 1 plus beta x squared divided by 2 factorial, like this. So I can expand, this is expansion of this. So by using this relationship, we are now getting ph equals to sigma times e raised to beta x, correct? So this can be also written as sigma beta times, what is the x here? The x that we have assumed is this one, right? ln h by h naught. So I have to write ln h by h naught, which by using the law of logarithm I can shift this as make and power. So I'm going to get is sigma naught e raised to ln h upon h naught over beta, which is simply now sigma naught, this one is h upon h naught is beta. So this is the approximated version of our solution that we are getting, this one h naught beta, which is equals to sigma h upon h naught mu r over h naught. So this is the solution, and you know this term involves h naught. So this is the variation of the pressure with respect to height at the entry, correct? Because at the entry, when x equals to minus L, your h equals to h naught. So for the exit is similar here. For the exit, you just have P, this you can write as entry, P h exit equals to sigma h upon h1. Then you can write this power, which is mu r over again h1. Okay, so this is at the entry when x equals to 0. So these two are the final version of equation that we got. So this is the exact solution, and these are the approximated solution that we got by approximating certain values by using the Taylor series expansion. Now, how will you find that pressure is varies with h as well as also it varies with x? So if you remember, we have this diagram, correct? We have this type of diagram that we have drawn in the class, and I'm going to say that this is a entry point and this is a exit point. So we have fixed the coordinate as this one, x equals to minus L and x equals to 0 is the coordinate point. So if you see this carefully, at any instant which is x is greater than or equal to minus L, we can say is greater than minus L and less than 0, you will have h which lies less than and less than h0. So you can see here, this is your h0 over 2 and this is h1, right, over 2. So if this is a center line, so if this is the one, then you can say that your pressure from here, the pressure that you have depends on the thickness. It varies with respect to thickness as well as it varies across x. So it is also a function of x. So how do you translate this into p of x? Well, we know that this is a free variable, right? So in the class we have said h of x is satisfied with h1 plus delta h x squared upon L squared. So this is the variation of height. This height with respect to the x coordinate that we are trying to fix, and we have validated this, right, by substituting this one into this equations 1 2, then we are getting p h entry equals to sigma, then we are going to substitute this h1 plus h x squared divided by L squared. So this is the whole thing is our h, right? So I'm going to divide this and say h0, correct? Then raised to 2 mu r over h0. So this is the equation which uses this one, px at the entry now, because you can see the x is involved here. Similarly, we have px exit as I can write here like this, h1 plus delta h x squared upon L squared upon h1, then mu r over h1. So these are the variation, and I've successfully translated p of h to p of x. Okay, so this is the end of the equation that we have got, and this is how we do it. Okay, so thank you for listening and watching. Thank you.